Thanks a lot. So I just want to give an example and to show how the theory developed can be put in practice. But before, let me say something about nilpotent orbits, since several things were mentioned, but maybe let's put all together. And then we will pick a specific nilpotent orbit and we try to perform all the computations. So just want to remember that I briefly mentioned that if we have two elements in the same nilpotent orbits, then the corresponding W-algebras are isomorphic. So let's talk a little bit about the structure of nilpotent orbits, and then let's pick one. So okay, let's take G to be finite dimensional reductive Lie algebra. And then the set of all nilpotent elements, let's denote it by N, it is a cone. So it's called the nilpotent cone. And it's the disjoint union of some orbits. Let me say X for some representatives X. Let's make an example to view this more specifically. So let's think of SL2 as in the two-dimensional representation. So 2 by 2 matrices, which have zero trace. So such a matrix is nilpotent if the determinant is zero. So what is this nilpotent cone now? Is just given by all the triples X, Y, and Z, such that X squared is minus Y times Z. And then let's change coordinates. So maybe we send X to Y to Y plus Z and Z to Y minus Z. Just to make it, I mean, it's not, we already know what object is this, but just to make it a little bit more familiar. So then this is just the following surface. And if we think we are working over the real numbers, just to draw a picture, then this is, I mean, we can really visualize it is a cone. And there are some, so this cone is the union of two orbits. Let's write this down. So one orbit is given by the apex of this cone. It's just the orbit of the zero matrix. And then, for example, I don't know, maybe here there is the matrix in Jordan form, which has one nilpotent Jordan block of size 2. And there is this other orbit. So basically, the orbit of the zero element is the apex, and the orbit of a non-trivial nilpotent element is the cone minus the apex. And what are the properties of these two orbits? So this is the unique orbit which contains just one element.
Sorry, orbit is the orbit under the joint action of the liquid.
Oh, yeah. I should have specified this. So let's say under the action of, so for GLN, SLN, it's not important, but let's say the adjoint group. The adjoint group is the image under the adjoint representation of the Lie group associated. The Lie group was Lie algebra is G.
This might be a dumb question, but is this nilpotent cone also a cone in the sense of it's closed under addition and multiplication by?
Yeah, exactly.
Okay,
any line,
great.
If you pick a nilpotent element, any multiple of this nilpotent element is still nilpotent. So
Great,
any line through the origin goes through. So in this case, this is just the SL2. So the adjoint group is more or less the group of automorphism of the Lie algebra G, but we want to remove some central element, like it's not SL2, but we are removing plus minus 1. But for G equal SLN, I mean, we get the same orbits if we pick G to be GLN, SLN, or PSLN. So in this case, the orbits are the same. But in general, for some simple algebras, situation may be a little bit different. And yeah, I was talking about this. So the property is this, it's unique with one element. And what about this orbit? So we have removed one point. So this is an open subset of the cone. So it's open. And as thanks for pointing out, So if an element is nilpotent, a multiple is nilpotent. So when we take the closure of this open set, we need to add 0. And if we add 0, we recover the whole nilpotent cone. So these are not features only for SL2. These are in general.
Daniela, is it open in G or is it just
Oh,
open
yeah,
in
open in N. Yeah,
in
the open
N.
and dense in N. Yeah, thanks. So more general, in this nilpotent cone, so there is a unique orbit with one element, and let's call it the 0 orbit. There is a unique orbit which is open and dense, and this is called the principal nilpotent orbit. This is the same as what Tibor called the regular nilpotent orbit in his talk. So let me just use this principal. It's the same as regular, same meaning. So let's denote by O prince. And then now we cannot appreciate the picture in SL2 since we only have these two orbits. But in some sense, this is the smallest possible, this is the largest possible, and there is a second largest one. So there is a unique orbit which is open and dense in N minus the principal nilpotent orbit. And this is called subprincipal or subregular. And then there is also, yes.
I think to have the unicity for the subregular, you need to assume that G is simple. Otherwise, you can take the product of one O sub and one O principal, and the contrary, and you get two.
And so it happens that we also have something which is the second smallest one. So let me just state this. We already observed that thanks to the remarks, 0 is contained in the closure of any nilpotent orbit. And then there is a non-trivial nilpotent orbit of minimal dimension. When I say non-trivial, different from the 0 orbit. And this also is unique. So this is called the minimal nilpotent orbit. And so it really behaves like the 0 orbit. So one can show that if we take the closure of some orbit, which is not 0, it contains the minimal nilpotent orbit. And the nilpotent orbit are have a partial ordering, let's say. And so what happens? What's the situation? We have this principal, which is bigger of the subprincipal. You have the 0 orbit and the minimal, which is bigger than the 0 orbit, and then we have some fuzzy structure in the middle. But there is a largest one, a second largest one, and a smallest and a second smallest one. And if we want to think in terms of some representative, like we have done in this example, so the sum of the Chevalier generator, negative or positive, is a representative for the principal nilpotent orbit. And for example, the lowest root vector is a representative for the minimal nilpotent orbit. And
excuse me, what is the partial order that you have on? What exactly?
yeah. Thanks for asking. Yeah, I forgot.
It might be helpful to use a different symbol for the partial ordering than to include.
Yeah. Thank you. Yeah, I think it's already clear that I'm very sloppy with the notations.
Little physicists here in secret.
And so, okay, now it was shown by Thibault this kind of way of realizing orbits using Young tableau. So this comes from the fact that we can associate, say, by fixing some representation, we can associate some partition to any nilpotent orbit. We'll just pick some representative. Let's call it F. We write F in Jordan form. So there will be a bunch of nilpotent blocks. And then we say that the partition corresponding to this orbit or element. It's just the sum of all these sizes of Jordan blocks. So what are the partitions corresponding to this case? Let's say for G equal SLN. So if we take the sum of all these Chevalier generator, we just get the partition N. So to the subprincipal corresponds to this partition. So if we take any representative in SLN of the subprincipal nilpotent orbit, its Jordan form is one block of size n minus 1 plus one block of size 1. And when I say block, they're all nilpotent, okay? The minimal corresponds to the following. So it's the sum of 2 plus 1 n minus 2 times. And the zero orbit is just the sum n equal 1 plus 1. Okay, so I say briefly in the, I use the fact that for principal nilpotent, the W algebra is the center of the universal enveloping algebra. For the zero orbit, it's just the universal enveloping algebra. So now let's try to see if we can describe what happens in the minimal, for the minimal nilpotent orbit. So that's the plan for today. But I thought it was useful to have an idea of what kind of example is interesting next, without just talking about this. Please.
And this one thing you said when you started.
Is this bijection with partitions only for A type?
It's not. It's
sorry.
It's bijection for SLN.
Okay.
For SON SPN, we go to partition with some symmetries.
Okay.
And then it's not useful for exceptional Lie algebra. I mean, it's one can do, but for example, the representation of E8, it's very, very big. There are other types of representation, but fixing some representation, we can always associate a partition looking at the Jordan form. Yeah, maybe this is. Thanks for asking. So it's one-to-one correspondence for, say, GLN, SLN. And then let's say need to restrict to, let me call them partition with symmetries. It doesn't make any sense. I know, I'm sorry, but for SON, SPN, SON, SPN. Somehow these symmetries are the same that define SON, SPN, but it doesn't make any sense. And yeah, there is, this famous book by Collingwood and McGovern, where you can find everything about nilpotent orbits in Lie algebras, and also the classification in exceptional case.
I think if Tomoyuki were here, he would say to be wary of that classification.
Oh, really?
He and Anne fell afoul of that, and it took them a long time to fix some of their results.
Okay. So let's be careful with the classification there. But at least the techniques, I think, are correct, and one can learn what techniques are used. Basically, for classical Lie algebra, it follows from work of constant and linking. Just assign a number to the linking diagram of G, and you know what kind of nilpotent orbits you have. And this number is called linking number. Okay, so I want to try to discuss, hope this motivated that after from the universal enveloping algebra, this is the second next example of W-algebras, at least for GLN. So let's study GLN, SLN is the same, but let's study this algebra. And just I want to say that what I'm going to say, it's, the final result is not new. These were already studied by Brandon and Klesher. I think it's 2006 paper. So these objects, W-algebras in type A, are related to certain objects called shifted Yangians. So the goal is to get this result and from a different point of view and explain how this can be generalized. Okay, so the first thing to do is encode all the data that I tried to explain in the second lecture, where there was a lot of heavy notation in one object. And this object is what Thibault drew, it's a Yann diagram. But unfortunately, I'm stick for simplicity to this linking grading. So it's a kind of very special Yann diagram. It's not a Yann diagram anymore. Actually, the Yann diagram is a special object, it's a special pyramid. So let's draw this object. What is this? So this base consists of 2 blocks, which corresponds to the first part of our partition. Then we add another block, and we keep doing that until we exhaust all our partitions. So this is something that we do for this partition, but we can be done in general. So this is called a pyramid. So it's the pyramid associated to this partition. And what's the difference between a Young diagram? So a Young diagram is a particular pyramid. So the properties of this is that it is symmetric. So let's draw some y-axis. If you change the shape of the pyramid, you are changing the grading of the Dinking diagram, of the Lie algebra. Fixing the Dinking diagram consists of choosing a symmetric partition, a symmetric pyramid. How to recover all the information? Let's draw also a horizontal line. Let's call this X. And let's say that our box have sides, length side 1. It's not really in scale, but so one thing that we need to do, we need to fix some vector space, and we need to choose, as I say, the standard representation if you want to write relations. So let's fix the standard representation. So this is just some n-dimensional vector space. We fix a basis. How do we fix a basis? Let's put some numbers on our boxes as we want. And there is no restriction. So let's say this is 1, this is 2, 3, up to n. So this means that vi is just some basis vector corresponding to the box I. Okay, now we have encoded our vector space in the pyramid. So what is an elementary matrix? So yeah, I mean, sorry for this very basic linear algebra. What does this elementary matrix do? It sends vk to vi, k is equal to j. Okay, now I'm sticking to this pyramid, but this works in general. So what does it mean? So let's have a look. Let's say this is k, j, and this is I. So we may think an elementary matrix as an arrow, which sends j, the vector vj to vi. Okay. So now that we have, I mean, this is something that you know very well. Now that we know how to represent elementary matrices, what is an important element in Jordan form, which has one Jordan block of sides 2 and n minus 1 Jordan block of sides 1. So this F minimal is the shift to the left. So what does it mean in terms of this picture? Let me draw only the non-trivial arrows. Everything else goes to 0. We can represent with this matrix once we have fixed a basis and we have assigned some numbers to the pyramid.
Sorry, just a comment. I mean, before you told us that the right representative was to use the lowest root vector, and this is a simple root vector.
Yeah, but if
it's
if
okay,
we can switch 2 with n and we get
yeah,
they're in the same. Yeah, this was just to give some abstract definition of this. Yeah, so as thanks for David for pointing out, it doesn't depend on the choice of the basis. Okay, just I fix some number for simplicity. So what else do we need? We need to build up an SL2 triple. So what is X? So X, let me first denote this. Xi is just the X coordinate of the center of the box. So this H, this diagonal element in the SL2 triple containing this F that we have construct is done as follows. It's just some diagonal matrix, which on each vector vi acts by multiplication twice the multiplication of the coordinate of its center. So now we can write it very easily. So on V1, it acts by multiplication 2 times 1/2, so it's 1. On V2, it acts by multiplication minus 2 times 1/2, it's minus 1. And then it acts as 0. So if you know about representation theory of SL2, I mean, it's quite obvious how to get these formulas. And this works in general, okay, this is just this particular case. So once we have F and H, we need to write down the corresponding gradings.
I don't know, what do you mean by works in general? What do you mean by works in general?
Oh, this procedure just define xi to be the coordinate at the center of the box.
But do you mean
and this formula works in
other ranks or in other types?
Oh, GLN, yeah, let's see, GLN. Oh, actually works, I think it works also for SON or SPN, but we need to be a bit careful. We need to write some
restrictions.
Symmetric with, now I use the word symmetric also there.
Symmetric with
symmetric with other symmetries, which comes from, I mean, once you have the classification and you write down the partition, it works in general. It works for anytime you fix a representation and you write your nilpotent element as a partition. It just depends on the representation. And so now now let me just switch, since I always use half of the eigenvalues. So I will call this 2x, okay? And I will use the ADX eigenspace decomposition rather than dividing by 2 every time. So how to get ADX eigenvalues? Well, now this is quite standard. So what is the action of this element x on the elementary matrix Eij? It's just xi minus xj Eij. So let's collect the grading into a matrix. I mean, this is just a way, it doesn't have much sense, but let me write it. So what I want to write in position 1, 1, the degree of E11. Okay, I hope it makes sense. So what's the degree of the matrix E11 with respect to the adjoint action of X? Is 0, and it's easy to get from this, just it's 1 minus 1. What's the degree of in position 1, 2? It's 1 minus 1, so it's 2, but we need to divide by 1/2. 2 divided by 2 is 1. And the next step, we need to divide by 1/2. Here we have minus 1/2, minus 1, and here we have 0. So the meaning of this matrix is in position ij, there is xi minus xj, which is equal to the ADX eigenvalue of Eij. Just to avoid some space, otherwise I need to write down all the. And I think we are done. No, yeah, the last piece of information is this shift matrix D. And then I think we have everything. So how to read the shift matrix from the pyramid? So again, in this case, for the standard representation, I wrote the explicit formula. It's a diagonal element. And this di has some combinatorial meaning. So we look at the box, I, and we look at how many boxes are entirely at the right of it. That's the number di. So the huge formula, which is written in terms of Casimir operators, becomes very simple in this case. So di is the number of boxes entirely, since there may be half shifts, entirely at the right of the box I. So let's write in our case what it is. So how many boxes at the right of 1? How many boxes at the right of 2? Well, there are a bunch of boxes, but they're not completely at the right. There is just 1. And up from 3 to n, there is nothing entirely at the right, because 1 is a half D. So this pyramid allows to write down all these combinatorial, all this object which I introduced last time in a kind of combinatorial way.
Minus 1 under the 1 over 2 of the second line.
Here?
So this we have minus 1 after 0. No, minus 1, 0 as we have, but after minus 1 was
second line.
yes,
minus 1, 0.
Because you have minus on edge, you have minus 1, and it's minus 1, minus 0, minus 1, minus 0. So it's supposed to be a line of minus 1. And in the second line, after the third column.
Changing the order.
Ah, sorry. Yeah, sorry, I forgot to write this. Yeah, I forgot to add a line. Thank you. Okay, other questions? Yeah, thanks for checking carefully. Okay, I think it's everything we need to write down the Lax operator. Maybe, yeah, I haven't described. Yeah, before going, we need also these spaces V minus and V plus, which appear in the definition of the Lax operator. So what are? And just remind ourselves, V minus is lowest weight vector. And what are the lowest weight vector that can be read in terms of this pyramid? Are kind of the leftmost column of boxes. And when I say boxes, I mean the corresponding vector Vi in the leftmost column. So in this case, it's just one-dimensional vector space. And similarly, highest weight vector will be the span of boxes in the rightmost column. And last time, thanks for pointing out, I made a mistake when I wrote the decomposition. So the decomposition is, which comes from SL2 theory, is the following. Okay, this can be seen, for example, in this case. So what is the kernel of F? We need to pick not only the leftmost column, but the left part of each, the left column of each partition. So now the kernel of F is the following. And the image of E, so you may think of E being the shift to the right, so just this vector. And similarly, the image of F is the shift to the left, so we can only reach 2. And the kernel is this, kernel of E.
Sorry, you just corrected the thing I'm gonna ask.
Thanks. Thank you.
Daniele?
Yeah.
About the lowest weight vectors, I mean, you have lots of like copies of the trivial representation. You don't want the lowest weight vectors in the trivial representation. You're excluding those, or?
Oh, no, I'm thinking of V as a whole representation.
A GLA representation.
Yeah, so the lowest weight will be -1/2.
Okay.
Yeah. In fact, if we want to take care of it, that was the mistake I made last time. We need to take all the lowest weight vector for each horizontal representation. That's the kernel of F.
Okay. So why do you then only have V2 for the lowest weight?
This?
Yeah. Why don't you have like V3 up to Vn?
Because
lowest weight vectors for other.
Because I want, just for V, just for the whole representation V.
Okay.
Not for each sub-representation. Okay. These are the spaces which appear in the definition of this quasi-determinant.
Okay.
And
sometimes SL2, sometimes GLA.
Yeah, sorry. So V minus is the space of lowest weight vector for the action of GLN. Kernel of F is the space of lowest weight vector for the action of SL2. This was the identity which comes from SL2 representation theory, which I brought wrongly last thing that last time I denoted this D is the depth, is the largest eigenvalue.
Daniele Valeri is asking whether or not the lowest weight vector should be Vn instead of V2. Do you want to just do the calculation quickly?
Yeah, I mean, it depends on the basis you choose. I denote this by 2, as you suggested, it was maybe better to call it N, but yeah, eventually the choice won't depend on the basis because we are writing down a Casimir. So just think of the labels that you give to the leftmost column.
Okay.
I hope it explains.
Yep, he says he sees it.
Okay. And one property that I use in some proof, and I don't know if it was clear enough. I just say that we can identify, let's see, let's start. Yeah. I wrote this is an isomorphism. I hope now it's clear in this example that it is an isomorphism. So F, if we restrict F to highest weight vectors, what does it do? It just sends to a lowest weight vector. So D is equal to 1 in this case.
The left one should be V minus.
V minus, yeah.
Thought it would be the left one.
Is it correct?
I don't know.
So it sends F is a shift to the left. So we send highest weight vector to.
You're acting with the identity on V minus.
Yeah, thank you.
Okay.
Thanks. Okay, thank you so much. and it works in general. It was something that I was trying to explain. With pyramids, I think it's very easy to get it. So let's write down this operator L. I think now really we have everything. So let's recall the definition. Yeah, when I write capital F, now it's just the image of F minimal in the representation. I'm using the same notation as in the abstract formulas. Then we don't need to take all the Casimir element, but just some part of it. And we need to add the shift matrix. And then we need to take the quasi-determinant in position V plus V minus. And I didn't do this computation, but I try to explain that when these are one-dimensional vector space, we recover this quasi-determinant as defined by Gert van der Retak, which was denoted by 1, 2. So now let's write down this. So we need to take only the elements which have degree less or equal than 1/2, which are almost everything except for this element. But remember that the Casimir is defined as the transpose. So there will be just an empty space here. And then we need to cap everything else. And let me see, I use some notation. Let me see if it's useful this time. Yeah, I don't know if it was a good idea. Let me see, I just do E plus 1. So this matrix that I'm writing is just Z plus U less or equal than 1/2. So let's say what are these E plus 1. So I just use this notation. Yeah, unfortunately, we had to fix a basis to write down, but otherwise it would have been much easier without. So this E plus 1 corresponds to these two columns that when we transpose in the Casimir appear to here. And similar, this is I plus. And then we have this block of zeros, which are denoted by capital E plus plus. Okay, so this takes care of the first and third term. Then we need to add F, which is the image of F min, which was this matrix E1, 2. So we need to add 1. And then we need to add the shift matrix, which is still here. So it just consists of writing this -1. And we need to compute this quasi-determinant. Okay, so this quasi-determinant in the formula that we wrote, it just consists in writing this as this is B. Let's call this D. And the remaining matrix.
Sorry, should that in E plus plus, do we start with E31 or E33?
E33, yes, thanks. And I think I denote the matrix by D and this by C. Okay, just to remind, this is equal to A minus B D inverse C. So now it's just a matter of computation and inverting this blue matrix and then expanding. And let me just write the result. I mean, formulas are not important. I just hope it's clear how to work this out. And let me write this as the final result as T1 of Z minus T2 of Z, T4 of Z inverse T3. You can perform the computation and check if what I wrote is correct, if you wish. Okay, apart from these formulas, which one can check, what is important is that these are all polynomials. And the final expression is a rational function in Z. So what we proved in the second lecture, I mean, what I hope you believe that, is L of Z is as coefficient in the W algebra, but as a Laurent series. Tensor this on from B minus to B plus, which now we can forget since this is C in this case. So let's forget about the homomorphism part. We just got a scalar. So then we cannot infer that T1, T2, T3, and T4 have coefficient in the W algebra. And in fact, the only thing that we can do is to expand this rational function, pick up a coefficient of this of a power of Z. This lies in the W algebra. So how can we extract all the generators of the W algebra from this? And the way to do is never expand. So never expand. We just need to use the properties of rational functions.
Can I ask another question? Yeah. Sorry, you may have mentioned this before, but I think I was a bit behind. What happened to the first column over there? You've got A, B, C, D, and the first column ignored. What's the deal?
Because it's in position 1, 2. So we need to.
This is position 1, 2.
Yeah. This is, so when we have this quasi-determinate position 1, 2, we pick the position 1, 2, and we call it A. The remaining part, B is all the orange one.
Okay,
yeah, sorry.
B and D include.
Yeah, all the color. Yeah, it was
all
unfortunate. Right. If I have choose E1N, it was much clearer.
No, that's better. Thanks.
These are together, and this D is a matrix, which we need to invert.
I understand the colors now. Yeah, no, it makes sense.
That's why I don't like to write it down in matrices, but I think it's more easy to visualize than write. So how to get the generators? That's the main question. Let me state maybe this result. General feature for any nilpotent type A was written this procedure in a paper with Alberto De Sole and Laura Fedele. So the fact is the following, that there exist polynomials. Let me note them by Wi of z. This quasi-determinant can be written as the following rational function. And all the coefficients of this Wi lie in the W algebra. As I say, formulas are not important. What is important is that somehow so finding a basic means finding a system of generators is defined as follows. So this is in Premet sense. So Premet studied and these W-algebras around 2000. What does it mean to find the basis in the Poincaré-Birkhoff-Bitz sense? It means that we need to find a map from the centralizer of F to the W-algebra with some properties. And the main difficulty here is that the W-algebra is not graded. It's just there is just a filtration. So let's say the main property is that, roughly speaking, if WA belongs to certain filter space, we want that the associated grade is a monomial. Okay, it's a linear monomial. So this is not sufficient. Then we also need to know that this span W in the PBW sense. Okay, why I'm saying this? Because from our pyramid, we can also understand a lot about the combinatorial properties of the centralizer. For example, we can write down explicitly, now there is any pyramid, but just looking at arrows, we can understand what are the arrows we commute with the shifting to the left. This is not too hard to do. So there is a very nice combinatorial description of this. And from this nice combinatorial description, for example, it turns out that this follows that if we want such an expression to be true, then W2 has to be constant in Z. So T2 is a vector. So, I mean, it's not important how we call this generator. It's -2. Anyway, there is something that is telling us this is wrong because this is something which contains Z. So it doesn't work. The abstract theory is telling us that this polynomial cannot lie in the W algebra. And then we are not so lost because what happens that now think of this as a matrix. Now we have just a 2 by 2 matrix because our partition had only 2 parts. In general, we may have a bigger matrix, but it doesn't matter. This is the step of the theorem. So we have a polynomial of order 1. We have a polynomial of order 1 here. And we would like something which has less order. So what do you do? I mean, if you're a student in linear algebra, the first thing that comes to mind is doing Gauss elimination. And magically, I mean, what is nice, if we apply Gauss elimination, then the result of our application lies in the W algebra. What does it mean in this particular example? So we could rephrase our proposition by stating that we have constructed, and let me just explain a few steps of the iteration. So this Premet map, now it's constructing just one step. If you have more parts, you apply this step, which I'm going to describe in the right bottom corner. and then you keep going until you reach. You apply all the steps to all the metrics. So how to get W? Okay, so we would like to replace T2, which is a polynomial of degree 1, with something which has degree 0, we expect. And we want to apply Gauss elimination with this T4. And then this is, I'm sorry for writing this, I apologize, but it has to be done at least once. So what is Gauss elimination? We need to perform division, right? So let's write this. Let's do also for this corner. So we got now two elements which have the right degree in Z. We show that this lies in the W algebra. Then we have a formula for W1. So I don't have time to go to the detail. This, of course, lies in the W algebra because L lies in the W algebra. Ah, yeah, the zero step is that show that T4 lies in the W algebra. Coefficient of T4 lie in the W algebra. And this is something that now finishes our job for this case, just because there are two parts in the partition. If there are more parts, you keep applying this procedure. So does it at least give some ideas on how the proof of the theorem works?
So how do you know that T4 lies in W?
Yeah, we need to prove. But this is it's related to something that Simon was asking, because now it is any pyramid. So there are this follows from some properties of the quasi-determinant, which are called hereditary, and it is as follows. So it means the following: if we take some matrix, we can take the quasi-determinant in steps, and we can also take submatrix and then take quasi-determinant. And if you look, this formula for T4 is the quasi-determinant of this matrix D in position 2, 2. So we can apply the same machinery which I described. So whenever we have a quasi-determinant, we know that it lies in the W algebra. Quasi-determinant of this ancestor matrix. So that's almost for free after showing that the quasi-determinant exists. That's the biggest part. In this case, it's easy to see that it exists because we just need to invert 1. Does it answer? It's the basic step of the recursion. And after you do this, then you don't need to do this step again because you rearrange the block in such a way that it lies in the W algebra. So you still have the recursive step. Are there other questions? Okay, now, so this, as I said, we can just rephrase it by claiming more abstract terms that we found a premet map, which is highly not unique. I mean, we can just multiply this on the right by something that commutes with W4 and put on the left. So it's not unique, but one such map exists. And then the question is now is to find the commutator of this Wi. And this is done using the RTT relation. So in this particular case, the RTT relations becomes the following identity. Okay. And now you proceed in the same spirit as we have done here. Never expand. So the left-hand side is a rational function. Set the expression of L in terms of the generators and solve for Wi, Wj. And I put solve in quotation mark. Why in quotation mark? Because you should think of this equation as a differential equation. So there is not a unique solution. But if we can find an initial data, it becomes something like a Cauchy problem. We can solve it uniquely. And to find the initial data, we need this information that T4 lies in the W algebra. It comes from a quasi-determinant, so it satisfies RTT. So the information of the relation of T4 allows to solve this, which is equal to W4, allows to solve this equation uniquely. Otherwise, you get some solution up to.
I have a conceptual question.
Yeah.
How do you know that all the relations are commutators?
How do you know?
How do you know that all the relations are commutators? I mean, abstractly, all I know about this W algebra is it's an associative algebra.
Yeah.
You've given us some generators, but couldn't there be higher order relations like cubic, quartic, or something awful?
Yeah, there cannot. Yeah, I don't remember the reason. If someone knows.
Not sure I understood the question correctly, but
Since we know that the PBW generators are in fact form in fact a PBW basis, if we have only the if we are able to say that we have all the commutators between the PBW generators, I think we know that we have all the information which is needed because we have an explicit basis. I don't know if it is.
Yeah, it's a good point. Now I don't remember why it's sufficient to just get the commutators.
We're working with sort of like a universal W algebra here, right?
Yeah.
It doesn't have to be simple.
No.
Okay.
Yeah, I think it's sufficient to know that there are no other relations in the universal enveloping algebra, but I don't remember the motivation. Yeah, of course, if you quotient, then there are other problems. And what kind of relation did we find? As I said, there was already some result, deep result by Brandon and Clasher. So the relations satisfied are kind of first stages. So Brandon and Clasher prove the following: there exists a surjective map on some object. Now we'll describe it to this W algebra. Actually, the result works for any f in type A, but this is the specific case to our example. So there will be different numbers here. So how is this object called? So this is called the shifted Yangian of level 2. So let me try to explain what this is. So this is a subalgebra of the usual Yangian. And yesterday I explained how to get a presentation of the Yangian, which was called the RTT presentation. But let's work with a different presentation, which is more similar to how we present Lie algebras. Namely, there is a triangular decomposition. Let me call it a triangular presentation. And what does it mean? It means instead of writing one series T, which satisfies this RTT relation, we write certain number of series. Let's say di of z, I from 1 to n. So let's think this is for Gln. And then we write ei and fi. This was n minus 1. On the blackboard, what these numbers are, otherwise we get confused. So n minus 1 is the height of the pyramid. So every time I make a mistake, you can correct. And 2 is the length of the base. So you can understand now how to generalize to any important element. And yeah, so this now goes from 1 to n minus 2. And this goes from, yeah, this also. So we should think of these DIs as generators of a Cartan subalgebra. And these EIFIs as generator of the nilpotent positive and negative nilpotent parts. As you may guess, these kind of generators are very useful to write down representation theory. So it looks really like the composition of a Lie algebra. I won't write down the formula because I don't remember. I don't know actually. But let me try to explain how to get this shifted Yangian. So we may imagine that this Yangian, the usual Yangian, corresponds to this object, to a rectangle of base 1 with n minus 1 boxes. I made it rectangular. Let's try to fill this rectangle with all our generators. So we put all the generators di in the base, and then we put the generators E1 here, F1 here, and so on. Okay, now we would like to shift. So what does it mean to shift graphically? We would like to shift and achieve our partition P. So what does it mean? It means that in some sense we would like to cancel a little bit of these boxes, in such a way that the final result looks a little bit more like our partition. Let me explain this with a lens. Let's put a lens on this, on some block. Let's put a lens here and let's start to write. So these are power series, remember, so EI of Z will be something like, I don't know, I1 Z inverse plus and so on, so on. And here let's write on the reverse order. So this will be F1 I of Z inverse plus dot dots. And imagine that each EI corresponds to some vertical. So let's put some slices, each one corresponding to EI1. I should have included maybe also Z inverse. Then EI2, and so on. Maybe these slices become smaller and smaller as Z becomes bigger, as N becomes bigger. And we do similar here. Let's see what we have done. We have done this procedure of erasing something. Let's do this again. So for example, what does it mean that we erase a little bit of this slice? We are forgetting F11. And since our pyramid is symmetric, we need to do the same here. So we are forgetting EI1. And how many elements we forget? Well, this is told us from the partition. And what does it mean forgetting in mathematics word? It means that we can shift the starting point of our generating series. So we define another generating series by shifting all our elements to the left, and then we forget about them. So we just multiply by some number, and then we take the negative part. So we are shifting our generating series, and we forget some of the generators. If we forget some of the generators, we get a subalgebra. Sorry, I don't have time to explain this. And the paper is by Brendan and Kreshevitz, very long and involved, but I hope this gives some ideas. The idea is to start from a big rectangle and eventually end up with our pyramid. And shifting just means that we are forgetting some generators, and this Ki depends actually on the high row of P. And it's not hard to guess what it is. It's just the scaling function of the distance from the largest part of the partition. But in this particular case, since the partition is symmetric, it's the same. If we take, for example, Young tableau as described by Thibault, we are not shifting on the left, we are only shifting on the right. So this Ki may be different in general. So this gives some idea of how this is constructed. Just forget about some generators. How we forget from some generators, this information is encoded by P. There is also two that we need to fix. This level, what is the level?
So Daniele, are these EIs and FIs, do they correspond to the boxes that you're trimming here? We don't have an E1 and an E2, is that right?
Say it again, please.
So the EIs and FIs only run from 1 up to n-2.
Yeah, because
should we think of them as being E3 up to En?
Yeah, exactly.
Because we want to have 2 at the bottom, right?
Yeah, exactly. So far we don't have 2, right? No. So that comes from now choosing this level. So I hope
okay.
I gave some some clown idea of how this is constructed, but it's, I mean, there are a lot of relations, there are a lot of explanation to be given. It's just some combinatoric, I mean, some subalgebra defined by some combinatorics of the pyramid. So I hope now we got this inside this. And now let's think this now belongs to this new pyramid. But still this now contains the old DIs. Here the generators have changed. I have just relabeled EI tilde, FI tilde. So we should also remember that there were 2 blocks in our partition, right? We really would like to draw a vertical line here. What does it mean? This in terms of our Yangian. So this is just the quotient of this shifted Yangian. Yeah, this is called shifted. And this is the quotient by some ideal. And the definition of I involves now the generators DI. So I'm not going to explain the definition. The idea is that we want to put some generators on the right, some on the left, and draw a vertical line. So really to get our pyramid P. And this is called shifted of level P. Okay, so what's the relation with this? Yeah, sorry for this very vague idea of what object it is. But there is a lot of combinatorics involved. So what's the relation with our matrix W? yeah, really we should think that our matrix W is more of a RTT presentation of this Yangian in the following sense. So up to multiplied by some powers of Z, since Brandon and Clash have always start with only consider formal series in Z inverse, why I have used in this definition Laurent series. But this is related to that operator Z minus delta, which I just wrote, but let me write it explicitly. So imagine that this W is a kind of RTT presentation. So how to get these generators in this case? Yeah, I shouldn't use the 1, the 2. So I really, so this E, remember that this E is a vector, so it contains all the vectors E I tilde. This D1 is a scalar, and this is a matrix and contain all the remaining DIs. And this is similar, it's a vertical vector. So it really tells us how to go from a kind of RTT to triangular decomposition. So eventually the objects are the same, as we should expect, since the result was already proved. And yeah, the objective of this study was try to expand to other types. So even though we got something on the other side, which, as Professor Arakawa mentioned yesterday, the map is not surjective, so we need to perform all this procedure to make it surjective. But yeah, I have no idea what object is on the Yangian side. Thanks a lot for the invitation and the opportunity.
Time for some questions.
It's not a very precise question, but all this construction work because we have a nice combinatorics for the classical types. Do you expect that this maybe could be generalized in an abstract way to any algebra using combinatorics on the root?
Yeah. So the construction of these generators works in any algebra.
Okay.
The problem is that to construct relations, as also David was mentioning yesterday, we are using the evaluation map, which I know only for Yangian or twisted Yangians. So this construction of the generators you can do in any algebra. Then probably there may be other ways to compute the relations.
So Vidas is asking in chat, do you know anything about the co-algebra structure on these W-algebras?
No. And yeah, I think the problem that there is no Yangian appearance in type BCD may be due to the fact that I hope there is a co-algebra structure, but it's not known yet.
More questions? Yes.
Can you say about applying?
Yeah, for rectangular nilpotent, the operator is constructed by you and Professor Molev. And what can I say? It's the following. Take G equal GLN. F is rectangular, means that the partition is all sides have the same, all parts have the same sides. So this operator L of Z was constructed by Professor Arakawa and Professor Molev. And we are talking about affine vertex algebra, okay? Affine W-algebra. Okay, and the idea is to use this row determinant. And the fact that even though the vertex algebra are non-associative, in that case, everything is associative and the definition works. So this is the first problem. So the first problem is non-associativity, and what's the meaning of quasi-determinant? But that issues can be solved easily. I mean, we can just give a linear algebra definition of this quasi-determinant, which does not involves associativity or computing inverses or inverting matrices, let's say, because that's the main problem. I can replace your construction, and what I can do is just so far, I mean, I can extend to, instead of having one part, just two parts. And then comes the second problems. So what are the OPs on this? I mean, this is a problem already in the rectangular case. But the hope was that, I mean, here we have the relation almost for free using this quasi-determinant formula. But using the alternative definition, it's very nice because it allows to show existence much easier than what I did. but it's not very useful to write down explicit formulas for the relations. So there are the alternate definition is not very good. But there are some results which related the affine Yangian not to the affine W-algebras, but to some associative algebra associated to that. So maybe that's the point of view to take care, because in that case, we have associativity, so we can construct the quasi-determinant. But even in that case, that it's not clear to me how to put back the relation to the vertex algebra. That's a very big problem. But I hope there is some room for exploration.
Can I ask just a brief one? So if we fix with the principal nilpotent, does this all reduce to Miura transform technology, or is it somehow different?
Oh, yeah, we can. We can. It's different from Miura transform.
Different.
Yeah, it's different.
Okay, interesting.
But it's the Miura transform is obtained, let's say, principal nilpotent. The Miura mapping, we have some expression for our Lax operator, and we try to factorize it, and then we get a map from some generators here.
Yes.
Can
we just move the camera? Yeah. Sorry.
And this is the Miura map. So it can be studied also using Lax operators. Comes from factorization of these Lax operators.
Yeah. Okay. All right. I think it's time for some morning tea. So thank you, everybody, and thank you very much.